All right, Gen Chem kids, we are going to practice some more ionic compounds today. Today we are going to add in yet another layer to it. We're going to use what are called polyatomic ions. Up until now, we have just done what we call binary compounds. I should probably define that again. So binary ionic compounds. Bi means two. So when we talk about binary ionic compounds, we are going to make ionic compounds with just two elements. So ionic compounds with just two elements. So when we do binary compounds, we always have a metal, that is our positive ion, and then we have our nonmetal, that is our negative ion, and we put those together to make that ionic compound. Today we're going to talk about polyatomic ions. So let's define polyatomic. Poly in Greek means many. Atomic means atoms. So these are ions made up of two or more atoms. Okay, two or more atoms, and they are ions. So that means that even though those atoms are bonded together, we still don't have the same number of protons as we have electrons. So we have an ionic charge over that polyatomic or that molecule, okay? So polyatomic ions are made of more than one atom. Okay, so usually it's two or three atoms. Okay, so we're going to do a few examples. We have SO4, so S and then 4 oxygens. This 4 tells me I've got 4 oxygens. Now this number here at the top, this tells me the charge. And it's a charge of -2, so I have 2 extra electrons. SO4 has a name, and it is called sulfate. Okay, CO3, -2, this is called carbonate. And if you cook, you might have used carbonate a lot. How many of you guys have used baking soda? Baking soda is just sodium bicarbonate. So you have a sodium, and then you have the bicarbonate ion. And that bicarbonate ion is a -1, and that sodium ion is a +1. And that's what you use to raise quick breads like muffins or sweetbreads like banana bread. Okay, we have our positive ion that we are going to use. This is ammonium. Okay, ammonium, 1 nitrogen and 4 hydrogens with a charge of +1. This is going to be the only positive ion that we really use in this class. There are other positive ions, but for the purpose of this class, this is the only one. All the rest are going to be negative. Then we have NO3, negative. Now notice with this negative, I did not put a number here. And also with this positive on the ammonium, I did not put a number here. That means it's 1. If I don't put a number, it means 1. So ammonium up here is charged a -1. Nitrate down here is charged ammonium is charged a +1. Nitrate is charged a -1. So this is nitrate. And you may have noticed, if you read ingredient lists on food, you may have noticed nitrates being used a lot to preserve meats. A lot of lunch meats, like sliced turkey or sliced ham, are preserved with nitrates. And then we have C2H3O2 with a -1 also. Some people write it like this, CH3COO. Both of these are the same. It's just how you write it. This is the inorganic chemistry way, and this is the organic chemistry way. But they mean the same thing. This is acetate. And you guys have all probably experienced acetate. If you've ever used vinegar or had some kind of a vinaigrette dressing on a salad, this acetate right here is what gives the vinegar that tart, that sour flavor. Okay? So let's move on just a little bit. I want to just skip a little bit and go to these polyatomic ions. This is a list of polyatomic ions and their charges so that you can have a list. And yes, I will be giving you a list to reference when you have quizzes. So don't worry that you have to memorize it, okay? So let's go through this really quickly. We have ammonium, we have nitrate, and we have nitrite. Now notice these are different with just one letter. Nitrate gives us 3 oxygens. Nitrite gives us 2 oxygens. So pay attention to the spelling and the verbiage, nitrate versus nitrite. Okay, so you've got to listen carefully and you've got to pay attention to the spelling. Okay, hypochlorite, ClO -1, chlorite, Cl2 -1, chlorate, ClO3, and perchlorate. So this basically tells us how many oxygens are on. Hypo means the smallest amount, chlorite means the next, chlorate means one more, and perchlorate means completely filled with oxygen. Okay? Hydroxide, we will use hydroxides a lot later on in the year. Hydroxides create basic solutions. So most of our bases are going to be hydroxide solutions. Cyanide, Cn -1. Acetate, this is what makes vinegar. Okay. Permanganate, MnO4 -1. This creates a lot of bright purples here. Carbonate, we use carbonate a lot in, as I said, like baking soda is sodium hydrogen carbonate or sodium bicarbonate. It goes by both names. That's why we have the bicarbonate. Notice we just put a hydrogen on here and it took that charge from a -2 to a -1, adding that hydrogen. Okay. We have sulfate, SO4 -2, and we have sulfite, SO3 -2. Now notice the 8 versus the 8 and the number of oxygens on there. We have bisulfate and we have bisulfite as well. So this is a group as well. We have chromate that creates a bright blue or a bright pink depending on how it's oxidized. We have dichromate. So notice dichromate tells us that there's 2 chromiums in there. Okay. We have peroxide, which is a -2 oxygen, O2. Now that gives us hydrogen peroxide when we put it with hydrogen. We have oxalate, which creates a very weak acid that we use in a lot of things. We have phosphate, which we use a lot in fertilizers to plant and make our plants grow stronger and produce more. We have hydrogen phosphate, and we have dihydrogen phosphate. So this is also a group here. And then we have silicate. Silicate is the ion that creates a lot of rocks. You will see a lot of geological formations, a lot of rocks are built with silicate. Okay, so this is just an overview of those polyatomics. Now, once again, you do not need to memorize these. These lists will be available for you, and I do have another list for you to use during your tests and your quizzes. Okay, let's go back and look at some of these examples. Now, Hopefully you remember that when we make ionic compounds, that the sum, and when we do sum, we use the Greek letter epsilon of all charges. The sum of all the charges, when we add up all the positives and all the negatives, it's got to equal 0. Okay? So we need to still, even with these polyatomics, we need to figure out what the ratio of that positive ion has to be with the ratio of the negative ion so the charges add up to 0. Okay? And to find that ratio, we are still going to take the charges and find the least common multiple between the positive and the negative charges. Okay? So let's do a few. What is the formula between sodium and nitrate? So let's look up our periodic table here. So let's look up nitrate first. If this is an alphabetical list, okay, so we have nitrate, NO3 -1. So I have an NO3 and I have a -1 charge. Let's look up sodium really quick. So if I look up sodium, this is kind of on the side, so you're going to have to tilt it. Sodium, let's get a highlighter pen out here. Sodium is right here. It's in our first column, and that first column has a charge of +1. So sodium is going to be a +1. Okay, what is the least common multiple between 1 and 1? Hopefully you said 1. So I need a charge of +1. So to get a charge of +1, I need 1 sodium. And I need a charge of -1, so I need 1 nitrate. So when I write this formula together, I am always going to put the metal first. Remember, the metal always comes first, or the positive ion comes first. And then you write the negative ion second, okay? That negative ion always has to come second. The negative ion comes second. Okay, so it's very much like finding things with the binary ones, but now we're using these groups, these polyatomics, and we use them as groups. Let's figure out the formula between calcium and nitrate. So we already know that the formula for nitrate is NO3 -1, so I can write that down already. Now let's look up calcium. So if I find calcium on this chart, it's right here. So this gives us a charge of +2 because it's in the second column. So calcium will have a charge of +2. Now let's find our least common multiple between 2 and 1. Hopefully you said 2. Our least common multiple is 2. So how many calciums do I need to have a +2 charge? I need 1 calcium to get to a +2 charge. How many nitrates do I need to get to a -2 charge? I need 2 of them. Now the thing is, I can't just do NO3 2 because I don't want 32 nitrates. So how do I show that I multiply that group by 2? In math, how do you show that you multiply a group of numbers by a coefficient? That's right, you put parentheses in there. So you're going to put parentheses around the whole entire group, showing that you are multiplying that whole group by 2. So when we write calcium nitrate, we are going to write calcium parentheses, NO3, close parentheses, and the subscript 2. Remember that subscript multiplies that whole entire parenthesis. So that means I'm going to have 1 calcium. That means I'm going to have 2 nitrogens, and it means I will have 6 oxygens because 2 times 3 is 6. Okay, so it doubles my whole nitrate group. All right, let's do some more. Now, here we go. We are going to do some practice with this thing. This has the ions right here, and it has the anions. And the first thing we've got to do is the charges are already given. So the first thing we have to do is figure out the least common multiple between the two charges. So let's look at this. Calcium has a positive 2. Hydroxide has a negative 1. So the least common multiple between 2 and 1 is 2. So that means I need 1 calcium, right? I'm going to need 1 calcium, and I'm going to need 2 hydroxides. Now remember, how do we multiply a group? We have to put parentheses around that group. Remember also that the positive ion always comes first, and the negative ion always comes second. Okay, so we want to write the positive ion first, and we need 1 of them. And then we need to group our hydroxides with a parentheses to show that we're multiplying it by 2. Now, when we name, we always give the metal name. We do the metal name. And then if it's a transition metal, and we'll get into a transition metal. If it's a transition metal, we might need to put in a Roman numeral to give the charge. But calcium is not a transition metal. Remember, it's an alkali earth metal because it's in the second column. The transition metal is just that rectangle metal in the middle of the periodic table, okay? And then we name the polyatomic. Okay, so we're going to have the metal name, and if it's a transition metal, we'll have to put a Roman numeral in there to give us the charge, and then we just name the polyatomic. So this would be calcium hydroxide. Now notice, I do not make it all one word. I do put a space here. So calcium space hydroxide. It's not all one word, okay? Now let's look at this next one. We have barium being a positive 2, and we have sulfate being a negative 2. So what is our least common multiple between 2 and 2? Hopefully you said 2. So, and there goes my computer. So to get to a positive 2, I need 1 barium, and to get to a negative 2, I need 1 sulfate group. Okay? Now, if you don't remember what sulfate looks like, or the name of sulfate, take some time and go to this chart. This is all alphabetical. So there's sulfate. SO4 negative 2, right there, sulfate. Okay, and I probably should have done that with hydroxide. Here's hydroxide. Okay, so metal first. We always write the metal first, and then sulfate. Now notice I didn't put any parentheses around the sulfate. And I didn't need to put parentheses around the sulfate because I'm not needing to multiply that group. So if I don't need to multiply that group, I don't need to put parentheses around it. So as we name this, Ba, the name of Ba is barium. Sulfate. Okay, let's look at this next one. NH4, positive 1. Let's look up on our NH4. Let's see. There it is. NH4, positive 1. It is ammonium. It is a positive 1, so we're going to name that ammonium. Now, when our polyatomic is the positive ion, we still just use the name of the polyatomic. So I know that I can call this ammonium something. So we can start there. Now, let's look at the charge. Positive 1, and we've got a negative 2. So if I look at my least common multiple between a 1 and a 2, I need to have 2. So how many positive 1s do I need to have a positive 2? I need 2 of them. And how many negative 2s do I need to have a negative 2? I need 1. So I'm going to need 2 ammoniums, and I'm going to need 2 dichromates. Let's look at the Cr2O7 here really quick. Cr2O7. Here we are, Cr2O7. It's dichromate. Okay, so we have our name, ammonium dichromate. Now let's figure out the formula. Let's put the dichromate here. Now be careful of your spelling, because when we do this in Canvas, it's going to be very specific to spelling. So make sure you put a space in here and make sure that you spell the name of the elements and the polyatomics correctly. Okay? So I needed 2 ammoniums. So to multiply a polyatomic, I need to put parentheses around it and then the subscript of how much I needed to multiply it by, which was 2. Then I only needed 1 dichromate. So I am going to put just 1 dichromate down. Or no, it's dichromate, not chromate. So this is a 7, sorry. Let's clean that up a little bit. Let's clean that up. Okay, so ammonium dichromate. Okay, let's look at this next one. We have silver, and we have C2H3O2. So let's look that up on our polyatomic. Oh, here we go. C2H3O2, also known as this. It goes by the name of acetate. Okay, so we know we have something acetate. So let's look at our chart. Ag is silver. It's a positive 1, and acetate is a negative 1. So what's our least common multiple of 1 and 1? Hopefully you said 1. So that means I need 1 silver and 1 acetate to balance this out. So 1 silver and 1 acetate. Okay, metal comes first. So silver, acetate. And yes, you can capitalize the second word if you want. If you don't want to capitalize the second word, you're fine. Okay, here we go. We have iron, and it's a +3, and we have sulfur, that's a -2. What's our least common multiple between 3 and 2? So let's do multiples. 3, 6, 9, 12. That should get us 2, 4, 6, 8. Do you guys see anything that matches so far? Do you see that the 6 matches? Okay, so the thing is, how many irons do I need to have a +6 charge? I need to have 2 irons. How many sulfides do I need to have a -6 charge? 2 times what gives me -6? I'm going to need 3 of them. So I'm going to need 2 irons, and I'm going to need 3 sulfurs. Now, iron here is in the middle of the periodic table. So let's look at where iron is. Iron's right here. That is part of our transition metals. So any of the metals that are in this middle block right here, they need Roman numerals. And those Roman numerals tell us the charge of that metal. There are a couple exceptions to that rule, though, and let's do the exceptions to that rule. Silver always has, silver always has a +1 charge. That's why I didn't put a Roman numeral of silver. Cadmium always has a +2, and zinc always has a +2, and aluminum always has a +3. Everything else, metal-wise, is going to need a Roman numeral with it. So that would include tin and bismuth. So all of these are going to need Roman numerals with them when they make compounds that are ionic. Okay? So let's go back to the iron here. Iron, it didn't heat my sulfide. So iron 2 irons and 3 sulfurs. Excuse me. Now, to write this, we need to designate that this iron has a +3 charge by Roman numerals. So hopefully you can figure out that you needed to, do you remember your Roman numerals? Let's just do a really big review. So 1 is going to look like an I. 2 is going to look like II. 3, III. 4, IB. 5, V. 6, VI. And you really don't need to have any Roman numerals beyond 6. Okay? So hopefully that was a lot of review for you. So we would call this iron. And we're going to put the Roman numerals in parentheses. So the Roman numerals tell us the charge of the metal. Okay? So they tell us the charge. Let's do charge of the metal. So that 3 tells us that the iron is a +3, and we're going to put it in parentheses, and then we end with sulfur. Now remember, this is a binary, so we need to end in "ide." So the root of sulfur is sulf, so we're going to call this sulfide. And my computer wants to think now. Sulfide. Okay, let's do a few more examples here. All right, so if I did, let's do a few more examples. Now, if I have some more polyatomics, let's do lead, and let's have it bound with sulfite. Okay, now we need to figure out that charge of the lead. And because lead, let's look at lead. Lead is one of these metals right here. It can have multiple charges. So what we need to do is we've got to figure out the charge by what it's bound to. So let's look at what it's bound to. It's bound to SO3. So let's find SO3. Okay, here we go. SO3, sulfite. It's a -2. So let's look at this. SO3 is a -2. This whole thing, PbSO3, has to add up to 0. So -2 plus what equals 0? What needs to be in there? Hopefully you said a +2. That means that this lead has to be a +2. So we would call this lead 2 because it's a +2 sulfite. Okay? Let's do another example here. Let's do OSO3. Now, osmium is another metal that is in the transition metal group. We do not know its charge at all, okay? And because we don't know its charge, we have to look at what it's bound to. So let's look at oxygen really quick. So if I look at where oxygen is on our periodic table, let's change the color here. Oxygen's right here. Remember, the halogens had a -1 charge right here. So that means this column has a -2 charge. So oxygen is going to be assigned a -2 charge. So let's see what that does. So if oxygen is a -2, right, and I've got 3 of them. So let's math this out really quick. So -2 times 3 will give me 6, -6, right? So my overall negative charge is -6. So -6 plus what is going to equal 0? Hopefully you said +6. So that means this osmium has to be a +6. So when we write that, is this going to let me scroll? No. We're going to say osmium 6 oxide. Okay, now let's do a couple of the other where I'm giving you the name and you come up with the formula. You guys ready for that? Okay, let's do this. What if I have copper 2 acetate? Okay, let's break this apart. Now, copper is part of that transition metal block. Once again. So, copper can have a +1 charge, or it can have a +2 charge. And because we put a Roman number 2 by it, that means we are dealing with the +2 copper. So, we've got copper being +2. Now we've got to look up acetate on our polyatomic chart. So let's look up acetate. So if I look up acetate, and if my brain remembers, acetate can be written 2 ways. Okay, for this purposes, we are going to use this, C2H3O2. And notice its charge is also -1. So let's write that down. C2H3O2 with a charge of -1. Okay, now we've got to figure out our least common multiple between these 2 charges. So I've got a +2 right here, and I've got a -1. So my LCM between 2 and 1 is 2. So how many coppers do I need to get to a charge of positive 2? Hopefully you said 1. How many negative 1 acetates do I need to get to a charge of negative 2? Hopefully you said 2, because 2 times negative 1 gives me negative 2. So I'm going to need 1 copper, and I'm going to need and I'm going to need 2 acetates. Now remember, when we multiply one of these polyatomics, in order to multiply a polyatomic, we've got to put parentheses around the whole polyatomic and put our multiplier as a subscript at the end. So here we go. 1 copper, and I'm going to multiply the acetate by putting it in a parenthesis and closing that parenthesis and putting that multiplier at the end as a subscript. Okay? Let's do another example here. Okay? Let's do iron 3 oxide. So, if I do, nope. I want to do iron 3 oxide. Now, you guys are pretty familiar with iron 3 oxide. In normal English vernacular, this is rust. Okay, so this is when that iron turns into rust. Iron 3 oxide is rust. So we know that the iron is a positive 3 because of that Roman numeral 3. Remember, the Roman numerals tell us the charge of the metal when we have a transition metal. Okay, so we know that we have iron plus 3. Now, oxide. Oxide isn't any element that I remember, but it ends in "ide." So what's the root ox come from? It comes from oxygen. So if I look at oxygen on the periodic table, sorry, the lunch bell just rang. Oxygen's right here, and it's a negative 2. So we know that oxygen is a negative 2. Whoa. Okay, so we know that the oxygen is a negative 2. So we need to find our least common multiple between 2 and 3. So if we look at our least common multiple between 2 and 3, we would get 6. So the question now becomes, how many iron plus 3s do I need to get to a positive 6? I need 2 of them, so I'm going to need 2 irons. How many oxygens am I going to need to get to a negative 6? 2 times 3 gives me 6, so I'm going to need 3 oxygens. So, yikes. So I will need 2 irons and 3 oxygens. So that is how you write the formula for iron 3 oxide, rust. Okay? So, hopefully this answered your question and you learned how to use polyatomics. Next time when we talk, we are now going to start on our nonmetals and start learning how to do the formulas for our nonmetal formulas. Okay? Let's see. Let's answer this last question here. When do I use Roman numerals? I use Roman numerals when I need to indicate the charge on a transition metal. Now remember, the transition metal, those are the ones in the middle of the periodic table in that kind of rectangular block. Now remember, there are some exceptions to that. The exceptions that do not need a Roman numeral. So let's see, let's spell it. Exceptions. The exceptions to that rule, there's 4 of them. We have silver, that's always a +1. We have zinc, that's always a +2. We have cadmium, that's always a +2. And we have aluminum, that is always a +3. Okay? Every other metal past the alkali and alkali earth metals are going to need a Roman numeral with them when you write the name. Okay? We are probably not going to be able to do the magnesium oxide lab just because of COVID. I will try and find a sim on PhET that will do that as well. Okay? Next time we will start talking about molecular substances and molecular compounds, writing formulas and formula names for them. So have a great day. We'll talk to you later. Bye.